So there's a number of camera influencers using numbers to sell cameras and camera features. And I get it, it's easy. Numbers are an easy reference point. But when people discuss bit numbers, it doesn't really tell the whole truth. 16-bit RAW, 12-bit RAW, you've heard it, you've probably repeated it, and the assumption baked into every camera review that discusses the raw numbers on a spec sheet is that the higher number is better. That's how our brain works. That's what we were taught since, year one arithmetic. 2's better than 1, 3's better than 2, etc., etc. That assumption is wrong. I mean, it's not always wrong, but it's dangerously incomplete without proper context. Today, what I'm going to try to do is explain why knowing the bit depth of a RAW format is meaningless without knowing one other critical piece of information. What's missing in the bigger numbers are always better argument is context. Something that most camera manufacturers, maybe not manufacturers, but most camera influencers and reviewers never give you is full context. The missing piece is this, not just what bit depth is the RAW format, but what type of RAW is it? Is it linear RAW or is it logarithmic RAW? Because this makes all the difference in understanding what value to actually assign to that number, to the 16-bit or the 12-bit. And once you understand the difference between linear RAW and logarithmic RAW, reading a spec sheets or paying attention to these reviews when it comes to RAW recording formats becomes a vastly different experience. Bit depth is the number of discrete values available to describe the brightness of a single pixel. I'll break it down like this. 8-bit gives you 256 values. 10-bit gives you 1024 values. 12-bit gives you 4096 values. 16-bit gives you 65,536 values. More values, more precision. That part is absolutely true. More bits can mean smoother gradients, better shadow detail, more room to push and pull your image in the grade. But, and it's a big but, here's what the spec sheet leaves out when it just gives you a bit depth number without the other piece of information. All of those bit numbers are not equal. A bit depth number tells you how many containers you have. It does not tell you how those containers are filled. Now, why is that important? The filling strategy, aka the encoding method, that changes everything about those bits. The two strategies are linear and logarithmic. So linear is one, logarithmic is the other, and they behave in totally different ways. Every modern digital cinema sensor or digital camera sensor is a linear device by nature. What do I mean by that? When light hits the sensor, it generates an electrical charge. That electrical charge is in direct proportion to the light. So double the light, double the charge. It's basic physics. But here's the problem. The way the sensor measures light and the way the human eye perceives light are completely different. Sensors count photons. Our eyes, these things, perceive contrast. And the human eye follows what's called the Weber-Fechner law. We, as human beings, are vastly more sensitive to changes in dark areas than bright ones. In a dark room, right, if this room is pitch black, and I walked in and lit a candle or struck a match, you would notice it immediately. But outside on a bright sunny day like it is outside in the city today, you'd barely register the difference between 1,000 lumen or a 1,200 lumen light. The shadow starvation problem. Here's where linear encoding breaks down. In a linear RAW file, code values are distributed the same way the sensor captures light, evenly and proportionally. And because each stop of light represents a doubling of intensity, the brightest stop in your scene consumes half of all the available code values. So you run out of numbers before you run out of stops of light. The bright part of your image gets thousands of code values to describe subtle highlight changes, gradations that the human eye cannot distinguish. and the shadow areas where your eyes are the most sensitive basically get starved to almost nothing. This is why linear RAW needs to be at least 16 bits at the bare minimum. So now that we know why 16-bit is key and why 16-bit is really just the bare minimum for linear RAW, let's look at the other encoding option, logarithmic encoding. Logarithmic encoding flips that logic entirely. Instead of allocating code values in proportion to physical light levels, a log curve redistributes them to roughly match how human vision perceives brightness. Each stop of dynamic range gets approximately the same number of code values. Every stop, bright highlights, deep shadows, gets roughly the same 292 values. The highlights lose the excess values they had under linear encoding, dropping from 2048 to 292. But you can't see the difference. The shadows then gain, jumping from 1 or 2 values to nearly 300. That's a difference you can absolutely see. So what you gain is smooth gradients, recoverable detail, a functional image. The result, a 12-bit logarithmic RAW file can capture 14 to 16 stops of dynamic range with full perceptual fidelity. So, since we're in the camera business or the filmmaking business, let's use a baseline everyone knows. So ARRI on the Alexa with the Aleph 3 sensor uses a 12-bit log encoding for the Aleph 3 sensors with 14 plus stops of dynamic range. The Alexa 35 with 17 plus stops of dynamic range only needs to move that logarithmic encoding up by 1 bit. So on the Alexa 35, you have a 13-bit logarithmic encoding to capture all of that range. Just one single additional bit, not a jump to 16, but just a jump from 12 to 13 because it's logarithmic. I would be wrong if I didn't address red. The elephant in the room that we need to address, arguably the brand that started the entire numbers war, whether we're talking about RAW or we're talking about resolution, Red Digital Cinema. They deserve their own segment because they've been doing something particularly interesting with their marketing for years. Red cameras are marketed as 16-bit linear RAW, and you know that framing is technically true, but only in a very narrow sense. The internal sensor ADC processes data at 16-bit linear resolution. Now, the pipeline starts at 16-bit linear, but what actually gets written to the card when you're looking at your redcode raw.r3d files is very different. The technical reality, which Red's own documentation and third-party analysis have confirmed, is that the recorded file behaves like a 12-bit floating point or log encoded data at the storage level. So while Red 16-bit claims refer to the internal processing pipeline, not the bit depth of the data written to your media. I'm just pointing out that the discrepancy that comes from looking at the numbers alone when you hear 16-bit linear RAW and you compare it to ARRI RAW on paper, you are not comparing the same thing. The question to ask, what is the bit depth of the encoding of the data on the card? The other thing we need to discuss is what happens when your camera outputs linear RAW. I know more cameras now are doing internal RAW, but we still have loads of cameras that require an external recorder. Let's start with the Sony FX6. Sony outputs 16-bit linear RAW via the camera's SDI to an external recorder. The recorder handles the encoding conversion, not the camera. That's important. The recorder is doing the encoding conversion, not the camera. Let's look at the other side of things. Let's look on the Panasonic side, the EVA1 camera that I am well versed in, and they chose to apply log encoding before the signal left the camera. The EVA1 solves this inside the camera. That's two fundamentally different approaches, and it changes what you can trust about what you're getting. So here's a bit of framework. And here's a checklist of what you should think about or run through every time you see a RAW format spec. I'll give you 3 easy things. Step 1, is it linear or logarithmic? Step 2, what is the bit depth recorded to the media? Step 3. Does the downstream recording format match the source encoding? Remember to ask, is that 16-bit, 14-bit, 12-bit raw, linear, or logarithmic? That's the important part.